Hello everybody, how's it going? Welcome back to another Geant4 video. Today I'm going to be showing off G4-Brems version 0.5.0 pre-release. And if you're new to this channel, G4-Brems is a Geant4 simulation of bremsstrahlung. So version 0.5.0 is really an accuracy release. So the goal of this release was to make the model a little bit more accurate to make it ready for the first actual release. All right, guys, so I went ahead and downloaded the assets here, the source code and the energy graph asset, and I extracted them here in my downloads folder. First, I'll demonstrate the project, and then I'll show you guys the changes to the code. So if you go here to the build directory and release, you can double click on the executable. Awesome, guys. So I can go ahead and run the test Mac file. So I'll click on test run, and it's pretty much similar to what you've seen in other releases. Not a lot has changed visually, but there's some little small subtle changes that we'll see soon. So one change that you'll notice, first of all, is now it tells you the elapsed time it takes per run. So in this test run, it shot 1,000 particles, 1,000 electrons, and it took 1.21 seconds. And then just like the last release, it generates this n-tuples root file. So if I double click on this, starts up a root session. Awesome. Then it pulls up my browser here with root. Can go here to energy. And here's the energy graph that's generated with the mean, standard deviation, and entries. And here we got position, X, Y, and Z. So in the last video, I briefly talked about this accurate run Mac file. And the goal of this accurate run script was to run 1 billion particles. So hopefully this would give us more of an accurate energy graph. And unfortunately, the accurate run in the last release didn't work for me. The reason why is because it just ran one run with 1 billion particles, and my computer couldn't handle all that in one run. So I switched up the file a little bit, and I'll show you guys the code, but I broke it down this time into segments. So this way it's not just one run all at once, it's smaller segments in a row. But long story short, if we go here to my downloads and to the energy graph asset, I was able to create a graph of the energy with 1 billion particles. So let's click on this. Here's just a PNG file, but you'll see here the entries, we got close to 1 billion here, and we get the energy spectrum, really nice. The mean is 1.237 MeV and standard deviation 1.109. Also included in this energy graph folder is a canvas root file. So this is a root macro file. So if you want to open this, you have to open in terminal this directory. Then if you have root installed on your computer, you just run root canvas.c. All right, guys, so here's the root viewer thing, and it's the same thing you just saw. So now if you want to have more control over what to do, we can do options. We can save as different type of file, PDF, GIF, JPEG, whatever we want. Let's check out the code here. So first thing I'm going to show off is the new accurate run Mac file. What you'll notice here is if you want to run this yourself, it might take around 1.5 hours. I let mine run overnight, so I don't know how long it took, but that was my estimate. So first thing you're going to see is we're going to open a different output file called accurate. The reason why is because G4-Brems is hard-coded to open an output file called n-tuples every time we have a run. So that's what this file is, n-tuples. One run will open this n-tuples file. But if you run the accurate run file, instead of opening that n-tuples file, it's going to open this file called accurate. And it's not going to open the file again every run. It's going to keep it open and do several runs before closing the file. So basically in this next line, we run the medium run Mac file 100 times. So let's look at the medium run Mac file. And basically it's just shooting 10 million particles. And this takes about almost 2 minutes, sometimes a little less than that. So it's going to run this 100 times. Then it's going to write to this accurate root file, and then it's going to close that file. So this method seemed to work a lot better than just cramming all billion electrons into one run. Breaking it up like this made it work a lot more consistently. All right, guys, let's go through the list of changes for this release. So the first change is there's an option for the user to input their own random seed. So by user, I meant the developer. So here in the main program file, if you scroll down here, in the other classes section, I have a random seed that I put in, just 1, 2, 3, 4, 5. Here we set that seed. That way, if you want to switch this up or create a random seed every run, you have the power to do so. So this just kind of gives the developer some more control, because before it had automatically generated a random seed, but it was the same every time. And I noticed the same particles were getting deflected in the same ways. And I wanted to have more control over the randomness. So that's why I added this little bit here. So the next couple of things that were changed, we changed the way we shot out the electrons. So if we go back to the code, go into primary generator action, this is the class where we start all the electrons shooting. And before, we had them all coming from one point in space and shooting exactly straight to the Z direction at the target. That's not really accurate to reality, though. In reality, a linear accelerator machine will get that electron beam down to a diameter of 1 millimeter. So what we did is here in the generate primaries function, we randomized the position within a 1 millimeter diameter. So the way I did this, I wanted to keep it very fast and very efficient. So I could have done like a sine, cosine type of thing to keep it within that circular radius, but instead I generate a random X value and a random Y value. So if you see here, we have a random value multiplied by the diameter minus the radius. So this is going to start from the center and go out 1 radius wide. So in the X direction, it's going to go out 1 radius, and then the Y. So that's why we create this square shape. And then here, I make sure that it stays within a circular shape. So here what I'm saying is, while x squared plus y squared is greater than r squared, so basically if the particle was outside that circular shape, I'm going to redo it, regenerate the x and y. But once they're inside that circle, I can move on. So every single event has a slightly different position inside that radius. The next thing I wanted to do was randomize the energy of the electron slightly. So before, I had every single electron was 6 MeV. And in reality, that's not really accurate either, because in a real machine, you can't get every single electron to be exactly the same energy. So based on a research article that I'll cite in my release notes, I gave the energy distribution a standard deviation of 0.127 MeV. So instead of just being exactly 6 MeV, it's going to be slightly varied, but very close to 6 MeV. So that's the way I randomize the particle generation just a little bit to make it more accurate. The next couple of things are related to the detector geometry. So if we go into detector construction, the first thing that I had on my list to do for a while was, instead of creating this whole apparatus in simulated air, I wanted it to be inside a vacuum. So to simulate this vacuum, I used the G4 galactic material, which is the closest thing that I could find that actually simulates a vacuum in Geant4. And then the last thing that I changed up in detector construction was our detector, the big box at the end that collects all the energy of the particles. I was looking up more about detectors, and I found out that in reality, they usually use lead to detect particles. So in reality, they'll use lead sheets mixed with some other kind of detecting material so that the particle can get slowed down by the lead and detected by the plastic or the xenon or whatever things that they use to record the energy of the particles. But in this project, I can use computer programming to take the energy from the particle as it hits the detector. So for now, I'm just modeling the detector as a solid block of lead to slow down those particles. So if you scroll down here, instead of tungsten, I just changed it to lead, which is using the G4-PB material in the materials manager. All right, everybody. So that concludes the demo of G4-Brems version 0.5.0, the accuracy release. Now, if you guys are still watching, I've been struggling with this question for a little while now, and I'd like to get your input. If anyone knows the answer to this, please let me know down in the comments or DM me on LinkedIn. So I'm still not super familiar with high energy particle physics, and there's something unexpected going on with my project. I've gone over it a lot of times. I don't think it's a bug, but if you guys could tell me what's going on, I'd really appreciate it. So I did a simulation with G4-Brems where I modeled different energies from 5 MeV all the way up to 40 MeV. So I have 5, 10, 15, 20, all the way up to 40. The reason why I did this was because here's a 5 MeV energy graph. And from all my research on bremsstrahlung, it's supposed to have the mean or the peak at 1/3 the max energy. So the max energy here is 5, and the mean is around 1, which is a little less than 1/3. So I'll go over to the 10 MeV, and if you see the 10 MeV, the mean is at 1.9. So it should be around 3.3 if it's going to be 1/3 of the energy. So I thought, okay, let me run some more simulations with higher energies to see what's going on. So here's the 15 MeV, and here you see something really weird's going on. We get a weird little plateau going on around 6 to 8 MeV. So we keep going to the 20 MeV simulation, and all of a sudden we have this second peak showing up around 12. Then we go to 25, the peak gets bigger, 30, 35, and finally 40. So I was not expecting this when I created this simulation. I thought every energy would have the similar energy distribution with its peak about 1/3 the total energy. But if any of you guys know what's going on here, if you guys know more about high energy interactions than I do, please leave a comment and I would really appreciate your input. So thank you guys again for watching my video. If this video helped you learn more about Geant4 and you would like to consider donating, please click one of those links down below in the description. But anyways, thank you guys so much for watching, and I'll see you later.